welcome to the third lecture for the module Space and Time, third lecture of term, where we'll be talking about Galilean Relativity or Galilean Space-Time. So, as you'll recall, the first two lectures of term were devoted to the question of whether space is absolute, or whether we should adopt a relationalist approach to the nature of space. And in the first lecture in particular, we saw an argument due to Newton that space is indeed absolute. This was the bucket argument, which relied on the fact that absolute acceleration seems to have empirically detectable consequences. So in the bucket experiment, it was the concavity of the surface of the water. In week two, we saw a very different sort of argument for the absolutism of space, and that was Kant's argument from incongruent counterparts. But in week two, we also examined a response to Newton, to the Newtonian argument for absolutism. And the response came out of the Leibniz-Clark correspondence. And the argument involved these shifted and boosted worlds. And the idea that shifted and boosted worlds only differ from our world in respect either of absolute position or the absolute velocity of the material universe. And yet such changes to absolute position and absolute velocity are empirically undetectable if something like Newtonian mechanics is true. So the thought there was, well, if they're empirically undetectable, then why should we posit them? That is, why should we posit absolute position and absolute velocity, or in other words, changing absolute position at all? Why not dispense with them and just go for a relationist ontology about space? So in a way, that sort of line of reasoning might be quite persuasive, but on the other hand, the Newtonian can point out to the fact that although absolute position and absolute velocity might seem not to have any empirical consequences if something like Newtonian mechanics is correct, nevertheless, absolute acceleration does, hence the bucket argument. And so the thought would be, well, the relationist just can't explain all of the phenomena that the absolutist can explain, because the absolutist can explain the curvature of the surface of the water in terms of the absolute acceleration of it. And so you might think, well, that means we've got to accept an absolutist position about space in its entirety, because after all, absolute acceleration is presumably just the first derivative of absolute velocity, which in turn is the first derivative of absolute position. So once you endorse absolute acceleration, it looks like you've got to endorse absolute velocity and absolute position, or in other words, you've got to endorse an absolutist view of the nature of space. Now, I guess that's sort of at the end of last week's lecture, I mentioned that, maybe it would be nice if we could have a sort of halfway house position or a compromise position, one that endorsed the notion that absolute acceleration exists so that we can explain what goes on in the bucket argument or the bucket experiment, and yet denied the existence of absolute position and absolute velocity, so that we don't have to live with the notion that there are infinitely many boosted and shifted worlds that are empirically indiscernible from our own. Now, that comment anticipated this week's topic, which concerns Galilean space-time, which aims to do precisely that. It aims to, in particular, dispense with absolute velocity. We'll see that whether it dispenses with absolute position is maybe a bit more subtle, but it wants to hold on to absolute acceleration. So we can definitely allow the sort of absolutist explanation of the results of the bucket experiment, whilst denying the possibility of infinitely many empirically indistinguishable boosted worlds. And then when it comes to shifted worlds, well, as we'll see, things are a bit more complex. But maybe this is progress against either Newtonian absolutism or Leibnizian relationalism. So we'll see this. And there's sort of another reason for introducing Galilean space-time, which is that it's not only is it in a way sort of a halfway house between the Newtonian absolutist position and the Leibnizian relationist position, but it's also sort of a halfway house between a sort of classical conception of space, Euclidean space, and the special relativistic conception of space-time, what's known in special relativity as Minkowski space-time. Now, special relativity is a topic that we'll come on to next week and the week after. But the introduction of the notion of Galilean space-time is going to be very helpful when it comes to understanding what's going on in special relativity. So there's a couple of good reasons for examining it. Okay, so I will switch to the handout now, and we'll be going through that. So let me just full screen this. Okay, so the topic's Galilean space-time. I've pretty much given that introduction that we'd ideally like maybe a compromise that can both account for the results in the bucket experiment, but also at least avoid boosted worlds and maybe shifted worlds too. And what we'll see is Galilean space-time seems to succeed in doing precisely that. So first we need a bit of introduction though, right? So in order to understand what Galilean space-time is, we need to understand some more basic principles of Galilean physics. So in particular, the notion of Galilean relativity and the notion of an inertial frame of reference. Now, both of these principles, in at least a very similar form to this, come up again in the context of special relativity and have an important role to play there. So this will help with understanding the material from next week and the week after. So Galileo was actually operating considerably before the Leibniz-Clarke debate. The notion of Galilean space-time, it's more of a kind of more modern articulation of what space-time might be like that relies on Galileo's ideas. It would, I think, be a bit of a stretch to say that Galileo himself advocated the notion of Galilean space-time as it's currently viewed in contemporary physics. So rather he had some interesting ideas that served as a basis for this conception of space-time. And the notion of relativity and of an inertial frame of reference were really the two key ideas. So as I say, this was prior to the Leibniz-Clarke debate by about 100 years, when Galileo defended the claim, which should seem familiar from the Leibniz-Clarke debate, that boosting a system, in other words, applying a uniform velocity to all of its material constituents, has no empirically discernible consequences. So we saw that on the assumption of a Euclidean space and the assumption of something like the Newtonian mechanics, then this is going to be true, right? So Galileo motivates this principle, this idea that boosts don't have empirically discernible consequences, by appealing to our knowledge of what it's like to travel on a ship. I suppose a sort of maybe a contemporary example would be traveling in an aircraft, maybe in a train, and so on. So what Galileo points out is that a ship that's in uniform motion, that is to say, it's moving at a constant velocity, it's not accelerating or decelerating, is a boosted system, essentially a boosted system, relative to a ship that's at absolute rest. So we just apply, in effect, the difference is just the application of a uniform velocity to all of the material constituents of the ship. Now, Galileo points out, and this is something we can empirically verify, that suppose you're situated below decks in this ship, and there's no windows in the cabin, so you can't sort of see whether you're moving with respect to the water and so on, then you won't be able to tell whether the ship is at absolute rest or in uniform motion. Now, of course, often when we are below decks in a ship, we can tell, but that's because typically we're not in. We don't have a case of uniform motion, right? So if the ship is speeding up or slowing down, or changing direction, or maybe being tilted from side to side by waves, then we don't have uniform motion. We have acceleration. And accelerations, as we've seen, are empirically detectable, according to Newtonian mechanics. So it's the accelerations that make you feel seasick. It's not the uniform motion. Okay, but if we do experience uniform motion, and sometimes on a smooth journey, you might get an approximation to this, at least after the journey started. And well before it finishes, so you're not speeding up or slowing down. So Galileo points out that if we have that sort of situation, then, for instance, it's no more effort to walk against the direction of travel than it is to walk in the direction of travel. It's the same either way. It's the same effort either way. So if you walk from the midpoint of the cabin to the edge that's in the direction of travel, that's going to take no more effort than walking from the midpoint of the cabin to the direction that's against the direction of travel. And it's the same effort in both directions, and it's the same effort as it would be if the ship were stationary rather than moving inertially. Similarly, you can perform experiments like dropping objects from the ceiling of the cabin, and what you'll find is that they fall in a straight line to the floor. So they don't curve away from the direction of travel or towards the direction of travel or anything like that. If you're accelerating, this will be different. But if you're in constant motion, uniform motion, then you'll get just a vertical drop, just as you would if the ship were at rest. Okay, so this leads to the principle of Galilean relativity, which says all experiments carried out in the two states, the one where the system's at rest and the one where it's moving at constant velocity, have exactly the same empirical or observable outcomes. So you just couldn't empirically detect whether the system is at absolute rest or in absolute motion, provided the motion is uniform, or indeed what uniform velocity the ship or the system is traveling at. So it could be traveling east at 5 miles an hour or 10 miles an hour or 30 miles an hour. You wouldn't be able to tell by performing experiments within the system. You'd have to look outside the system in order to tell whether it was moving inertially and what its inertial movement was. Okay. So Galilean relativity essentially follows from Newtonian mechanics. On assumptions that seem to be correct, namely that all forces due to collisions and the magnitude of those forces depend only on the relative velocities of the material objects involved in the collision. So this seems to be right. That if you've got a couple of, so I mean, I guess maybe a good example is in a car crash. So what really matters in determining the damage caused by the crash, so the forces in operation in the collision, is not the absolute velocity of the two cars, but rather their velocity in relation to one another. So I suppose, for instance, this means that if a car traveling at 100 miles an hour comes up to the back of a car traveling at 50 miles an hour and smashes into the back of it, well, the relative velocity of the first car relative to the second is 50 miles an hour. And you should observe the same consequences as if the first car had been traveling forwards at 25 miles an hour and the second car had been reversing at 25 miles an hour, which should also give you a relative velocity at 50 miles an hour. So assuming that the velocities are uniform, that's what you could expect. Okay, so you have this principle of Galilean relativity that seems to hold true, at least if Newtonian mechanics is correct, that whether a system is at absolute rest or in uniform motion, or indeed what uniform motion it's in, is empirically indiscernible. And we'll see that something very similar actually holds in special relativity. And so this isn't sort of very dependent upon the precise truth of Newtonian mechanics. Actually, other plausible candidates for what the fundamental physics of the universe might look like also give similar, or in some cases the same, relativity result. Okay, so if you're a relationist, of course, so the absolutist will say, look, there's a matter of fact about whether the ship is moving or not, because in one case it's moving with respect to absolute space, in the other it's not moving with respect to absolute space. Of course, the relationist can make exactly the same discriminations, because when it comes to a ship, right, the ship isn't all that exists in the universe. So the relationist can say, look, in one case the ship is stationary relative to, for instance, the shore or maybe the water, and in the other case it's moving inertially with respect to the shore and the water. So no one's in any doubt that there is a difference between the stationary ship and the moving ship. The point is just that if we're within the ship, then we can't empirically discern the difference. Obviously, if we look outside, then we immediately can. But note that, and this is where the sort of Leibniz-Clark debate becomes of relevance. So if you sort of generalize the case of the ship to the absolute, to the entire universe, the entire material universe, then the idea is that according to Galilean relativity, you couldn't empirically distinguish the case where the entire material universe is at absolute rest from the state in which it's in absolute inertial motion, which is precisely the point that Clark makes in the correspondence between himself and Leibniz. And in that case, you don't have any sort of external material reference point to sort of check whether the whole system is moving or not. Now, the relationists, because of the fact that there's no relational movement or difference in relational movement in the case of if you like, a stationary universe versus a boosted universe, actually wants to say that the distinction isn't really a distinction. There's no metaphysical difference between the two cases, whereas the absolutist wants to say that there is, as we've seen. Okay, anyway, so Galilean relativity, so this is another important concept. It appeals to the notion of an inertial frame of reference. And again, as I say, we'll see that this comes up in the context of special relativity. So an inertial frame of reference, and this just transfers over actually directly and without modification to special relativity. Any object that has constant velocity is an inertial frame of reference. So the ship, if it's in uniform motion, or if it's at absolute rest, because again, that's constant velocity, it's just zero constant velocity. Any such system is an inertial frame of reference. So there's this interesting fact about inertial frames of reference that within the inertial frame, empirical experiments can't discern the differences between the frames, the differences in inertial motion. Okay, so let's start to think more about, so we've got this sort of Galilean principle of relativity and the notion of inertial frame of reference on the table now. Now let's think about how these are going to contribute towards what's known as Galilean space-time. Now, one interesting distinction is that in the context of talking about Newton and the debate between Leibniz and Clarke, and when we were talking about Euclid, we were talking about space rather than space-time. And actually now we'll start to talk more about space-time as the relation between the two becomes ever more important. Now, having said that, we can coherently talk about Newtonian space-time. There's no reason we shouldn't. It's just that the spatial and temporal dimensions have a sort of clearer separation in, if you like, Newtonian Euclidean mechanics than they do when it comes to Galilean physics or special relativity. So let's start with the sort of presuppositions that Newton himself made, right? So he actually assumes not only that space is substantival, substance-like or absolute, but he supposes that points in space persist over time. That is to say, they retain their identity over time. So each point in space doesn't exist only for a moment, but rather continues to exist over time. So this is actually critical to make sense of notions like absolute rest, right? So to remain in absolute rest is to occupy literally the same set of points in space, that is the same spatial region, over time. That's what it is to stay at rest. It's to stay in the same place. But you can only stay in the same place if places continue to exist over time, right? If a place that exists at one time no longer exists immediately after, then we can't make sense of the notion of an object staying in the same place over time, and hence, for instance, being an absolute rest. And I mean, it's also needed to make sense of inertial motion. So we'll see basically in order to make sense of an object moving inertially at uniform velocity under Newtonian mechanics, well, the idea of inertial motion is going to be the idea that an object travels the same distance or equal distances in equal amounts of time. And we'll see that in order to make sense of that, we're going to have to be able to re-identify spatial points over time. But we'll come back to that in a second. Okay. So, assuming we do allow, as Newton wanted to, that spatial points persist identically over time, then we can make sense of the idea that each material object has a trajectory through absolute space. So a set of points that it exists, that it occupies over time. So it might occupy region A at one time, at time 1, region B at time 2, region C at time 3. Then the world line of the object is just going to consist of A at time 1, B at time 2, C at time 3, and so on. Now, we can represent the world line of an object by representing the location that the object successively occupies in space as time goes on, right? Now, to do this, we use a space-time diagram. So we'll become familiar with these over term. From next week onwards, we'll often make use of so-called Minkowski space-time diagrams. What we're doing right now is somewhat different. It's not a Minkowski space-time diagram, but it's a space-time diagram that's apt to thinking about objects in a Newtonian context. So, of course, when we draw a space-time diagram, we're a bit limited, right? Because space is presumed normally to have 3 dimensions. Time is normally presumed to be a 4th dimension. So what we're trying to represent when we represent space-time is something 4-dimensional. But the trouble is that normally when we're trying to provide a representation of this, we only have something 2-dimensional, like a piece of paper or maybe a whiteboard to work with. So actually what we're trying to do is give a representation of 4-dimensional space-time in 2 dimensions. So obviously there's some simplifications that are going to go on. So when it comes to representing a Newtonian space-time, what we're actually going to do is we're going to represent space as 2-dimensional. So we're sort of going to ignore the 3rd dimension to make this representable at all. And we're going to sort of try to represent the 4th dimension by stacking 2-dimensional representations of space on top of one another. So this is what's going on in figure 1. So each of the blue boxes is a 2-dimensional representation of 3-dimensional space. Now, you can think of each of the boxes as representing 3-dimensional space at a particular time. So the bottom one is a representation of space at t1, time t1. The second, a representation of space at the later time, t2. So we've got the arrow of time showing which ones are later and which ones are earlier. And then finally, the third box represents space as it is at time t3. Now, of course, according to Newton, space itself persists over time. So actually there's not going to be any change in the sort of shape or look of space itself over time in this diagram. But what can change over time, of course, is the position of objects within space. So that's certainly something that can change. So it's possible, obviously, for material objects to move location within space as time goes on. Or they might not, they might remain stationary. Okay, so I mean, there's lots of simplification going on here, obviously, besides the sort of attempt to represent something four-dimensional using what's effectively two dimensions plus a sort of stacking. Other limitations are, for instance, the fact that, for here, for instance, I've represented 3 times. I could have represented more, but I can only sort of do this finitely. And actually, we don't really want to presume that there's only a finite number of points in time or moments in time, right? So it might be, well, firstly, it might be that time is infinitely extended either forwards or backwards, so there's no beginning or end of time, right? So you might think that, although it turns out to be controversial, that view. But maybe a little less controversially, you might think that time's infinitely divisible. Now, again, that's not totally controversy free, but it's arguable that time's infinitely divisible. So, obviously we can't represent all the infinitely many times that are in between T1 and T2 on a sheet of paper. Okay. So yeah, lots of simplification going on. But I mean, that's sort of okay as long as we don't let ourselves be misled by the simplification. Okay, so then with Newtonian mechanics, or some Newtonian assumptions about space-time, we assume that the points in space, so any point within the bottom box, persists over time and is identical to a point in the middle box and the top box. And the convention is that the identical points differ vertically from one another. So they're vertical from one another in the space-time diagram. So in the case of, A, this is supposed to be the world line of an object that's stationary. Now, the idea is that if we assume that points in space differ only in a vertical movement from the same points in space at different times in our diagram, then an object that's at absolute rest is going to be represented by a vertical world line. So that's just showing that it occupies exactly the same set of points in space over time, right? So the points that it occupies down the bottom are the same points that it occupies in the middle at the later time T2, and the same as the points that it occupies at the even later time T3. Okay. Whereas with B, what we have is an object, and same is true of C actually, an object in motion, right? So the set of points that it occupies at T1 is different from the set of points that it occupies at T2, which differs again from the set of points that it occupies at T3. So that's what it is to move, right? Presumably to occupy different points in space at different times. Okay. Now, so there's an interesting difference not only between A and B within a Newtonian space-time diagram. So A is at rest; it's occupying the same points at different times. B is in motion; it's occupying different points at different times. But another interesting distinction is between B and C, right? So although both of them are occupying different points at different times, in other words, they're both moving, the line B is straight, whereas the line C is curved, right? Now, straight lines in a Newtonian space-time diagram correspond to world lines of objects that are in constant motion, in inertial or uniform motion, that is, traveling at uniform velocity. In the case of A, that's zero velocity. In the case of B, that's a positive velocity, but a uniform one. And basically the idea here is that if the line's straight, then the object is traveling equal distances in equal times. So assuming of course the interval between the represented times are identical, so we're assuming that the difference in time elapsed between t1 and t2 is the same as the time elapsed between t2 and t3. So the distance between the point occupied by the object tracing the world line B at t1 and the position that it occupies at t2 is supposed to be the same as the difference between the distance between the region that it occupies at t2 and the region that it occupies at t3. So it's traveling equal distances in equal times, and hence why the line's straight. When it comes to the object whose world line is C, well, the curvature indicates or corresponds to the fact that it's not the case that it's traveling equal distances in equal times. So this is an example of an object that's accelerating in the sense of picking up speed, right? So the distance between the points that it occupies at t1 and those that it occupies at t2 is less than the distance between between the set of points that it occupies at t2 and the set of points that it occupies at t3. So the object C is accelerating in the sense that it's picking up speed over time. Okay. Now, of course, a decelerating object could also be represented. That would be one that traveled a decreasing amount of distance in equal intervals of time. So if the difference between its t1 position and its t2 position were greater than its the difference between its t2 position and its t3 position. And we could also represent another form of acceleration, which is change in direction, right? So an example would be a circular motion, so the sort of motion that a particular part of the water in the bucket experiment makes. Now that would, if we were to draw it in a Newtonian space-time diagram, that the world line would look like a corkscrew. Okay, so they're quite helpful for thinking about the way the states of objects as they progress through time, the space-time diagrams. Now, that's Newtonian space-time, right? With the assumption that there's identity of points in space across time. And we'll see that Galilean space-time drops that assumption, right? So Galilean space-time drops the assumption that there's identity between spatial points at different times. Okay. Well, what does that mean? What happens if we do that, right? Well, first of all, as hopefully seems fairly clear, we're going to lose our ability to define a notion of absolute rest, right? So we said that in Newtonian space-time, we could say that A was at absolute rest, and that's because it occupies the same points at T1, T2, and T3. So it's not moving. But if we drop the assumption that there's any identity between points that exist at T1, T2, and T3, then we can no longer say that A occupies the same points at T1, T2, and T3, right? So we lose the ability to talk about absolute rest. And remember, Leibniz, for instance, wants to drop or reject the notion of absolute rest. And of course, we saw that the notion of absolute rest, it might, could be problematic, right? If we want to distinguish absolute rest from absolute motion, because we get a sort of boost argument that might be thought problematic. So you might think, okay, great, we're getting rid of absolute rest. That was a notion of something that was empirically undetectable. So maybe it's a good thing we've got rid of it. Okay, we'll come back to that in a moment. Okay. So I suppose just to be perfectly clear, obviously, if we reject identity across times, identity of spatial points across times, then having given up on absolute rest, we therefore lose the distinction between absolute rest and inertial movement, right? So we can't say that A is at absolute rest because of this failure of identity of spatial points over time. So there's no sense in which A is the one that's at rest, whereas B is the one that's in inertial motion. We can't assign any clear meaning to the notion that either of them are at absolute rest, right? We're denying the very notion of absolute rest. What we can do, though, is distinguish between. So remember, absolute rest is one form of inertial movement. It's the case where the absolute inertial velocity is zero. So we can still make sense of inertial movement, even if we can't retain the notion of absolute rest. And in general, in Galilean space-time, inertial movement is still going to correspond to straight lines through space-time, whereas acceleration can be distinguished. So we retain a distinction between inertial movement, an object that's moving inertially has a straight world line, and acceleration, an object that's accelerating has a non-straight world line in a Galilean space-time diagram. Okay. Now, so this, and I should say, look, the representation of Galilean space-time via a Galilean space-time diagram actually sort of visually is just the same as the representation of Newtonian space-time. So figure 1 could actually equally serve as a representation of Galilean space-time as it does as a representation of Newtonian space-time. The only difference is we've got to sort of drop an assumption that we're making about the diagram, namely that parts of the boxes that are separated only by a vertical distance represent identical spatial points. So if we drop that assumption, then we can interpret what's represented as Galilean space-time. Okay, right. So you might think, okay, so right, maybe we've lost the distinction between absolute rest and, if you like, positive inertial movement, and maybe that's no bad thing, as maybe the boost argument shows us. But on the other hand, it looks like we've got a distinction between inertial movements and acceleration, because we have the difference between straight and curved world lines. And maybe that's a good thing, right? Because after all, Newtonian mechanics shows us that, thinking about the bucket experiment again, shows us that accelerations can have empirical consequences. And so maybe we do want to retain the distinction between inertial motion and acceleration. So maybe Galilean Space-Time gets things just right. It is the best of both worlds. We hold on to the notion of absolute acceleration without having to endorse the notion of absolute rest, or a distinction between absolute rest and absolute motion. Okay, so you might think, well, okay, now this is a bit weird, because you might think, well, isn't acceleration just the derivative of absolute motion? And isn't motion just the derivative of position? So you might think, well, just because of the definition of acceleration, if we're going to hold on to the notion of absolute acceleration, which is represented by an object that traverses a curved world line, doesn't this just force us ultimately to accept the notion of absolute position? Well, I mean, not necessarily. So what the Galilean's going to do is the Galilean's going to say, I'm not defining acceleration in the standard way. What I'm going to do is I'm going to take acceleration just to mean having a curved or non-straight world line, right? So I'm not going to say, look, we have a notion of absolute position. It's understood in terms of the first derivative of absolute velocity and the second derivative of absolute position. Rather, I'm just going to define acceleration, or what it is for an object to accelerate, as the object's having a curved world line, and the degree of curvature and the nature of the curvature determines the degree and the nature of the acceleration. So we talked about the difference between the world line of an object that is gaining speed over time and the world line of an object that's losing speed over time, and the world line of an object that's changing direction over time. So we can make sense of all these things, all these notions, all these types of acceleration, just in terms of the shapes of the world line, without referencing absolute position or absolute velocity. Okay. Now, okay, so you might then think, well, okay, interesting, but what does it mean for an object to have a curved world line? Like, how do we tell, right? So, and okay, we can draw it on a bit of paper. We can draw a curve on a bit of paper, but I mean, you might, for instance, be thinking, it sort of could be easy to be misled by the drawing on the bit of paper, right? In particular, if there are no facts about identity of points across time, spatial points across time in Galilean space-time, then actually what really is the shape of a world line, or the curvature of a world line, telling us, right? It seems just to be, it must maybe an artifact of the representation. After all, since we can't really identify points across space-time, why should we think that actually really the distance travelled between T1 and T2 is less than the distance travelled between T2 and T3, really it's only if it's, or at least at first glance, it would appear that only if we can re-identify spatial points across time can we talk about the distance between those spatial points across time and compare the distances traveled by objects across time. Otherwise, the curvature of the line might just look like an artifact of the way we've chosen to draw the picture. So this is something we'll return to in a moment. And there is something to this worry. And yeah, I mean, potentially this is a problem for Galilean space-time, as we'll see. Okay, so but bracket that for a moment, and we just want to make some sort of comments on the ontological implications of Galilean space-time. So Galilean space-time is still really a kind of substantivalist view of space-time, space and time. It's there might be some concessions to the relationist. For instance, that we don't distinguish between absolute rest and uniform motion. But it's still, I think, more like a substantivalist view than a relationist view. So, for instance, absolute acceleration, as we've been seeing, is defined in terms of having a curved trajectory through space-time. But that seems to presuppose that there is such thing as space-time for the object or the world line to have a curved trajectory through. So the curvature is understood with respect to space-time. And so it is an absolute notion rather than a merely relational notion. Although we've been largely focusing on space and whether space is absolute, we can also see that in Galilean space-time, time must be supposed to be absolute, because we're supposing all the time that it makes sense to talk about the amount of time that's elapsed between two states, so that we can, for instance, say that an equal amount of time has elapsed between T1 and T2 as has elapsed between T2 and T3. So the Galilean makes no attempt to dispense with the notion of absolute time. Okay. And another kind of structural feature of Galilean space-time that again suggests the Galilean is treating space-time as substance-like is that it's assumed that there's a unique way of partitioning, or in the jargon, foliating space-time into sets of simultaneous points. In other words, time slices or simultaneity slices. So, there's actually quite, and this is one difference we'll see with special relativity and Minkowski space-time diagrams. In a Galilean space-time diagram, just like in a Euclidean space-time diagram, there's quite a strong separation still between space and time, right? So we assume that each blue box represents, if you like, a time slice of the universe. So a set of spatial points that stand in spatial relations to one another at a particular time. So, the bottom box is space as it exists at T1. The middle one is space as it exists at T2. So we're supposing that, it just makes sense to think of, a load of spatial points that exist simultaneous with one another and stand in spatial relations to one another. And moreover, actually, the Galilean, and this is connected with the principle of Galilean relativity, right? That inertial motions don't make a difference to the empirical results of experiments. the Galilean assumes that space as it exists at each of these times has a Euclidean structure. So this is a similar assumption to one that the Newtonian makes. So there's no deviation yet from the supposition of a Euclidean structure, which, well, we'll see a deviation from that when it comes to, especially to general relativity. But, if we're assuming that space is Euclidean, then we're assuming there is a thing that's Euclidean, so we're treating space as object-like, as something absolute. Okay. Okay. So it's worth pointing out that if we endorse something like the Galilean picture rather than the standard Euclidean picture, then obviously, as we've said, we're going to have to do a little bit of rethinking of our notion of acceleration. So acceleration isn't simply defined in terms of velocity and position anymore, but rather is defined in terms of curvature. Now, it turns out that, sort of generally speaking, we can reformulate Newtonian mechanics in the terms of Galilean space-time as opposed to Newtonian space-time, which presupposes identity of points over time. So basically the sort of, we do everything instead of appealing to notions of for instance, absolute motion or absolute acceleration per se. We're going to do things in terms of curvature. Curvature, obviously, positive curvature corresponds to acceleration, or non-zero curvature corresponds to acceleration, I should say. So curvature is going to be a surrogate for the sort of classic notion of acceleration, which is defined in terms of velocity and position. So one way of thinking about Newton's first law, formulated in maybe terms appropriate to Galilean space-time, it would just say that an object traverses a straight world line unless it's acted upon by a force. So if you recall, the sort of original formulation says that the object moves inertially unless acted upon by a force. So yeah, I mean, basically, we just retain that, but we say what we mean by inertial movement is not traveling the same distance in the same amount of time, because that becomes problematic if we can't re-identify space-time points over time, but rather we say it's moving inertially if it's traversing a straight world line. So an object traverses a straight world line unless it's acted upon by force. And Newton's second law, again, we preserve, but with the kind of caveat that we're defining acceleration in terms of curvature rather than in terms of velocity, and then ultimately in terms of position. So, to make it explicit, you can reformulate Newton's second law that says force equals mass multiplied by some measure of curvature, some appropriate measure of curvature, just to make the point that that's how we're understanding acceleration, and we're not simply understanding it as in terms of derivatives from position and velocity. Okay. So yeah, okay, so maybe Galilean space-time, maybe it allows us to have our cake and eat it. So, for the Galilean, there's no such thing as absolute velocity. There are no absolute velocities. we can distinguish inertial movement from acceleration, right? And that's just the difference between a straight world line and a curved world line. But we can't talk about absolute velocities, though. So in order to talk about absolute velocity, we would need a sort of, if you like, the one way of thinking about it would be if we have a world line that we could say is a world line of an object at absolute rest, then the degree of absolute velocity could be understood in the space-time diagram as the degree of tilt of the world line of the object compared to the one that's at absolute rest. But we've lost the notion of absolute rest. So now we can't make sense of a notion of absolute velocity. We can only talk about the degree to which world lines tilt relative to one another, rather than making sense of a notion of absolute tilt. So we've lost the notion of absolute velocity. So again, like, maybe that's good, right? Because we avoid this problem about boosted worlds. We don't have to acknowledge that there are, there can be differences in absolute velocities. We just have to allow that there can be difference in relative velocities. Differences in relative velocities are empirically detectable. Differences in absolute velocities, if they existed, wouldn't be. But on the other hand, we do retain a notion of absolute acceleration, defined as curvature of the world line of the object, and that is arguably a good thing because it allows us to explain the empirical results we get in cases like Newton's bucket experiment. Okay, so is this the best of both worlds? Or maybe does this mean that we should just endorse Galilean Space-Time? Well, unfortunately, arguably not, right? So there are still problems that Galilean Space-Time faces. Right, so I sort of alluded to this earlier and said I'd come back to it, and now I'm coming back to it. So if you endorse Galilean space-time, you still face something like a shift argument. I mean, actually, you face the shift argument basically in its original form, because there's a sense in which really, so Galilean space-time, it gets rid of the distinction between absolute rest and absolute motion. It can't make that distinction. There are just relative absolute motions. But it doesn't get rid of the notion of absolute position. So if you think about how the Galilean thinks about space at any given time, well, they think of it as absolute. We've made that point already. So they think of it as an absolute entity that has a Euclidean structure. So in that respect, the Galilean's assumption is the same as the Newtonian's assumption. It just differs from the Newtonian assumption in what it says about whether we can identify spatial points over time. But, focusing on a particular time, since we have an absolute space existing at any given time, a shift makes sense, right? So we can talk about at any particular time the entire material contents of the universe, or the entire material universe, being shifted by a particular vector that is uniformly shifted, and so that's a possibility. Is implied by the assumptions that the Galilean makes about the nature of space-time. And yet, as we've seen, under anything like Newtonian mechanics, such a shift is empirically undetectable. Then so we sort of open up the possibility that someone like Leibniz is going to say, well, we should drop this, right? Because we shouldn't posit structure to the universe that doesn't have any empirical consequences, doesn't explain anything empirically. So we've still got the shift argument, even though we've overcome the boost argument. Okay, good. Now, I say we've overcome the boost argument. Now, there's actually also a little bit of subtlety here. So Dasgupta, so you may have come across this in the reading for this week, argues that although by adopting Galilean Space-Time, we overcome the sort of standard boost argument, there's still a sort of close argument that applies to Galilean Space-Time, and he calls this the tilt argument. So his idea is that a universe in which all world lines are uniformly tilted over represents a distinct possibility in Galilean space-time, because what a tilt means is that each object now has a different trajectory through space-time, and he argues trajectory is something that is still defined in Galilean space-time. So the point is that these tilts, which look like if we imagine the space-time diagram to represent Newtonian space-time, then a tilt would look very much the same as a boost or exactly the same, in fact, as a boost in Newtonian space-time, and again would be empirically undetectable. So maybe the Galilean is committed to infinitely many empirically indistinguishable tilt worlds, and that might be thought problematic. So I mean, I guess that this depends on some technicalities, and maybe is a little bit controversial, right? So in particular, it's going to depend upon whether Galilean space-time really does make sense of a notion of absolute trajectory through space-time. So I'll refer you to the sort of details of the Dasgupta article if you want to follow that up, since we're low on time now. Now, I guess there's also this sort of circularity worry that I alluded to earlier. So there's this sort of worry that, curvature's doing a lot of work, right? So we're understanding acceleration in terms of curvature. But can we actually make proper sense of the curvature of the world line of an object if we don't identify spatial points over time, right? So let me sort of put it another way from the way I put it earlier. So if we're not supposing that the spatial points at T2 are identical to the spatial points at T1 that they're vertically separated from, and likewise when it comes to T2 and T3, then actually there's no reason to draw the diagram as this sort of neat stack, right? We would be just as well justified in shifting the T2 box to the left or to the right, and likewise with the T3 box, because we're just no longer making the assumption about the identity of vertically separated points. And remember, the box is a bit of an artifact because the space is supposed to be Euclidean, so it's infinite. So yeah, again, sort of shifts of the boxes to the left or the right, look perfectly reasonable. But obviously, if we shift the boxes to the left or the right, then the shape of the lines change, right? Whether they're curved, what extent they're curved, what type of curve they have. So, you might think, well, curvature is kind of an artifact of the Galilean space-time diagram, and you might say, well, if the Galileans going to appeal to curvature, then how are they going to understand curvature, given that they've dispensed with the identity of spatial points over time. And there's a sort of worry here that maybe there's a sort of circularity or in some way this is problematic. So arguably, whether a world line is straight or curved is empirically undetectable, right? So start by thinking of an analogy, right? So imagine you're in a spaceship and you keep seeing but you can't see anything apart from some other spaceships that keep coming in to view and going out of view again. Now, so it seems that perfectly possible that you shouldn't be able to tell whether the reason these other spaceships were moving in and out of view was because you were on a straight trajectory and they were on a curved trajectory, or whether it was they who were on the straight trajectory and you were on the curved trajectory. So I've attempted to represent what I'm talking about in the figure on the handout. So there's these two sort of hypotheses about why you see these spaceships coming into and going out of view. So the first could be you're on a straight trajectory and then spaceship A is on a curved trajectory and whooshes in and goes out again. Likewise for B and C. Or it could be that you're on a curved trajectory and they're on straight trajectories. And either way, you'd observe the same thing. You'd briefly observe each of these spaceships. But that doesn't tell you who's on the curved and who's on the straight trajectory, or indeed whether there's any absolute matter of fact about this, as the Galilean would say that there is. So I guess there's sort of maybe a sort of more general way of putting this is that you might think, well, look, how can we define the difference between a straight line and a curved line, which seems to be very important to Galilean space-time. When it comes to curved lines, we're not defining in terms of derivatives from velocity and position. A sort of geometric way that you can distinguish a curved line from a straight line is kind of by comparing lines, by drawing tangents. That would be a sort of geometric way of measuring curvature and distinguishing curved from non-curved lines. But this is a comparative process, right? So you've got to know which is the straight. If you're going to take a tangent, then you're going to have to know which is the straight line and which is the curved line. But that's kind of up in the air right now in Galilean space-time. We're looking for a way of defining or distinguishing the difference between straight and curved lines. Once we have a line that's known to be straight, then we can use it to measure curvature in other lines by taking tangents. But we're sort of one step back from that. We don't yet know which lines are straight and which ones are curved. Okay, so you might say, okay, well, look, we can tell which lines are straight and which lines are curved because curvature has empirical consequences, right? So if you're for instance, in the spaceship example, the idea would be that you'd be able to tell between the scenario depicted on the left-hand side and the one depicted on the right-hand side, because on the left-hand side you're moving inertially, and so you won't get effects due to acceleration, whereas on the right-hand side you're accelerating, and so you will get these effects. So it'd just be like the difference between the feeling of moving smoothly along a straight train track moving around a bend, right? So you can feel some of the forces associated with moving around the bend. So you can feel the difference, for instance, and likewise you can perform various experiments that would show you the difference. But so yes, they could argue that, but I mean, there's a sort of interesting circularity there, right? Because in Newtonian mechanics, we are supposed to be. I mean, one way of thinking about it is that we are explaining the empirical effects of accelerations in terms of the accelerations, right? So we explain why we feel a difference between when the train's moving inertially and when it's moving around a bend. We explain the difference between the water being flat and the water having a concave surface in terms of the acceleration of the water. So if we now, though, define acceleration in terms of the curvature of the world line, and we define the curvature of the world line in terms of the empirical consequences, then it looks like we're sort of going around in a circle, right? So we're explaining the inertial effects in terms of the curvature of the world line, and we're explaining the curvature of the world line in terms of the inertial effects. So you might think there's a sort of maybe a problematic circularity going on here. Okay. So, maybe there are ways of resisting this. So you might say, look, all we need is a kind of sort of coherence between what we say about space-time and what a mechanic says, so that they form a sort of coherent bundle, right? So we can identify the inertial effects with curved world lines and not experiencing those effects with the straight world lines. It doesn't really matter what explains what the direction of explanation is. It's enough that the sort of two go together. Like if we see some effects, then we just say we're on a curved world line, and if we don't, we just say we're on a straight world line. And then if asked to explain the effects, well, we say the effects are the consequence of acceleration or being on a curved world line. So it's a circularity, but you might say, the circularity is not problematic. It's a virtuous circularity, not a vicious circularity, something like that. But I mean, I suppose the sort of, the issue is that things sort of look undetermined. So yeah, I guess it is coherent to package Galilean mechanics. Sorry, I should say Galilean space-time with Newtonian mechanics. But this circularity might alert us to the fact that maybe there's another way of doing things, right? Maybe we could give a different mechanics together with different posits about the structure of space-time, and we'd have another compatible bundle of views. But maybe we want to know what the world's really like, and we don't just want a consistent theory, because maybe there are multiple consistent theories, and we want to know which one's in some sense true. Okay, so there are some worries about, suffice to say, about Galilean mechanics, but in a way, it's kind of a staging post on the way to so Galilean space-time, so kind of staging post on the way to Minkowski space-time. These are interesting worries, and one thing that will be sort of interesting to keep track of is whether these same sorts of worries re-arise when we make the leap to Minkowski space-time, as we will do next week, or whether some of them are resolved. Okay, but certainly it's interesting to think about Galilean space-time in its own right. It promises this kind of nice trade-off between a kind of classical absolutist view and a classical relationist view. But, as you might expect in philosophy and metaphysics, nothing's really straightforward. And, there are arguable drawbacks to Galilean space-time in its own right. Okay, thank you. I will speak to some of you again tomorrow, and most of you, many of you, again next week. Okay, thanks. Bye.